Cool. So once again, thanks, Ekhtiar and the organizers for having us. I organized JuliaCon a few months ago, and I know how hard it is to organize online conferences this year, particularly since none of us have any experience organizing conferences of this nature. So thanks a lot for your hard work. I know how difficult it is to, do things in these 2020 times. So today I want to talk to you about Julia. And in the next 30 minutes, I probably won't be able to convince you to drop everything and do Julia 100%. That's not feasible. But what I do intend is at least to give you a sense of why Julia is interesting, right? So I hope that at the end of this period, you will have enough of an interest to go and explore Julia by yourself and, write some code, maybe translate some of your own models and see how it can help you and be a good addition to your tool set. And if I can do that, then that will be time well spent, right? So the first sort of high level advertisement of Julia is that Julia solves the two language problem. That is, in some sense, the reason why Julia was created by its inventors, right? So the idea being that historically, a lot of scientific computing uses two different languages. So you write the sort of core algorithms in C or C++ or Fortran, and then you write some kind of a wrapper in Python or R or SAS or MATLAB, right? And that's how most scientific computing has been done for the last 50 years, pretty much, right? So if you use NumPy, which I suppose most of you do, NumPy is very easy to use. It's simple functions that are very fast, but all the actual logic in NumPy is written in C, right? And that works for a lot of what people want to do. Similarly, R, SAS, MATLAB have similar models, right? And what Julia brings to the table is the idea that you can write everything from your core low-level algorithms right up to your user-facing high-level models in a single language. And that allows you to be more productive, to move quicker, to write models and deploy models much faster than you would otherwise. And that's, in a nutshell, is the promise of Julia. And so the next sort of 15, 20 minutes of the talk, I hope to show you how and why Julia does this, right? How does it say that it solves this two language problem? So to begin with, a few logos, just to show you that Julia is not as much of a niche as maybe some of you think. It's used widely both in industry and in academia. There are universities doing courses in Julia. There are researchers writing their thesis in Julia, and there are people in the corporate world deploying their solutions in Julia. For a relatively young language, and also for a language that doesn't have a big company behind it, we think Julia has done pretty well. Julia has been in the public domain for about 8 years now. It was released publicly in 2012. And the founders have been working on the language for about 10 years now. So in language terms, it is pretty young. Python's a 30-year language at this point. And so, given how young it is, I think it's, doing pretty well for itself, right? There are plenty of books in Julia now, so learning it is easy. There are books for beginner programmers, so learning Julia as your first language, right up to domain-specific books that focus on using Julia for uh, specific kinds of science. So, for example, linear algebra or computer vision. Uh, And of course, there are best-in-class packages in many domains. So I think the basic idea that I want to leave you with is that Julia is growing. It's not a niche anymore, and it is very likely that if you want to learn or move your work to Julia, you will find lots of resources that allow you to do that. Right. So, having said that, uh, mostly by way of background, let's dive into what makes Julia special, right? Why is Julia a language by itself? Why is it, for example, not a way of compiling R or Python, right? Why isn't it like, something like PyPy or, a different compilation mode for Python? Why is it not, taking the R language and using LLVM to compile it, right? So the reason why, Julia is different is that it follows a very unique paradigm of programming called multiple dispatch. And what multiple dispatch does is that at runtime, it specializes functions based on the types of the function arguments. So if you define a function called add, for example, that takes two arguments, right? So the plus or the add function always takes two arguments. And multiple dispatch basically allows us to specialize the implementation of that function based on either of those two arguments. So so plus, as I said, takes two arguments, the first and the second. And multiple dispatch allows us to specialize that function based on both of those arguments, right? And the specialization is done at runtime, not at compile time. And that's how it is, for example, different from sort of function overrides in Java or C++, right? In that the specialization happens at runtime. So what's the big deal with that, right? It sounds like an esoteric compiler technology. Why would any of you care? Well, on screen, I have two examples that show you the native code that is generated when you add two numbers in Julia. The first one on the left is adding two integers, 1 and 2. And the second one on the right is adding two complex numbers, 1 plus 2i and 2 plus 4i, right? And Julia allows us to see the native code that is actually running on the CPU. And you will notice that the native code that is generated is different. And not only is it different, it is very specialized, right? And so in the first case in the left, you see there is a integer add operation. So it says add RDI and RSI, which are two integers on the CPU. And the add is the integer add operation on the CPU, right? So the compiler has figured out that we are adding two integers. And so it is doing an integer addition on the CPU. And you will notice that there is no type check anywhere in the compiled code, right? So all the type checks to see if a is an integer and if 2 is an integer has been compiled out. On the other hand, if you look on the right, where we are adding two complex numbers, right? These two complex numbers are composed of two sets of integers each, right? So 1 and 2 for A and 2 and 4 for B. And so if you look at the native code again, you have two integer additions. There's add RDI and RDX and add RSI and RCX, right? And so again, the compiler has figured out that, A is a complex number that is composed of two integers. B is a complex number that is composed of two integers. And so on the CPU, you can just do two integer additions, and that will, um, you know, add these two complex numbers. And again, all the type checks have been compiled out, and the code that runs in the CPU is very fast and very specialized, right? And the ability to do this at runtime is what makes Julia special. This ability to um, this ability to compile code at runtime to be very specialized for the types of the inputs that you are passing in your code is what makes Julia special, right? And we will talk a little bit later about how this contrasts specifically to some other languages, right? And we will circle back to this idea. We will circle back to this idea in a few minutes, right? Now, having said that, this idea of specialization, how does it matter in sort of large large code bases, right? Sorry for my spelling, but moving on. There are a couple of ideas here. One is that there is this idea called the expression problem, which says that if you have a code base, you can often imagine a code base to be a set of operations that operate on a set of types. So for example, your operations could be addition, multiplication, division, right? Integer division. And your types could be integers, floats, matrices, dates, right? And this is something particular in mathematical programming where, mathematics is like that, where you have an addition, and addition can mean different things for different things, can mean different things for different types. So adding two Booleans is very different from adding two dates or adding two big integers or adding two big floats, right? And this is something that you find very often in mathematical programming, where when you say adding, you say, what am I adding, right? Adding two matrices is completely different from adding two floats. And there is this idea called the expression problem where in functional languages, it is very easy to add new operations, right? While in object-oriented languages, it is much easier to add new data types. So if you have adding on, if your language defines adding integers and floats, right? Then if you want to add matrices, then object-oriented languages make it easier to add new data types. But if you have integers and floats and only addition defined, functional languages make it easier to add multiplication and integer division and subtraction much easier on your existing data types, right? But multiple dispatch makes it easier to add both, right? And this is one of the key reasons why Julia is so great for scientific computing, for mathematical programming. And some of this, you have to take my word for it, because in some sense, you have to program it yourself to really see the benefit. And I hope you do. But I think this is one of the sort of big reasons why Julia is designed in the way that it is. And this is the reason why 10 years ago, it was felt that we needed to develop a new language rather than, figure out a new way of compiling R or Python, right? And so, again, drilling down a little bit, what's the big deal, right? Why does it matter to you, right? And this is one example of why it matters. So most of you have probably used one of PyTorch or TensorFlow, and if you go to their GitHub repos, you will see that these repos are composed of about equal amounts of C and Python code. On the other hand, Flux, which is Julia's deep learning framework, is composed 100% of Julia code, right? There is no C or C++, and yet Flux in most cases is as fast as PyTorch or TensorFlow, right? Uh, and it does that by being 100% Julia, and that includes actually doing the auto differentiation, doing GPU programming, and all of that can be done using just pure Julia code, right? Uh, Another reason why this matters, and sort of drawing, taking that same argument, the ability to do multiple dispatch, the ability to do everything in one language makes it easy to interoperate very large packages, right? So you're not in this situation where you have NumPy and Cython and SciPy, and you're worrying about whether a NumPy array can be sent to a SciPy model, right? Or can you use Cython arrays and NumPy algorithms, right? So these are a couple of examples. One is a recent tweet that I saw saying somebody solved oscillator using differential equations and then solved the flow over that using a using a using a package called GridGap that is somewhat similar to PyMC. It does sort of Bayesian analysis, right? And these are two completely separate packages, very large packages, but you can interoperate the two. Another example is a package in Julia called Neural PDE that basically takes a differential equation solver that is written in Julia and uses Flux, which is our deep learning framework. And so, within a Flux model, one of the nodes in the Flux model is a PDE solver, right? And that just works without having to do any work. And so this ability to interoperate very large pieces of software is one of the key things that Julia enables us to do. Another interesting place in Julia where a lot of work is happening is auto differentiation. Most of you would have worked in deep learning frameworks, and that auto differentiation is a key element of deep learning. And we think of auto differentiation as a compiler problem, and the idea that all of Julia is written in Julia, a large part of the compiler is also written in Julia, allows us to really innovate in making really fast auto difference tools that can work with any Julia function, right? So Julia's auto differentiation works across any Julia loop, for example. A for loop or a while loop in Julia can be auto differentiated without any trouble. And so that, again, is something powerful that comes out of this whole multiple dispatch, single language paradigm, right? Now, of course, lots of people come to Julia for performance. And there are, if you look in search online, there are tons of performance analysis that shows, Julia is faster than some other thing. And so I think, it is now, I hope I don't have to convince many people that Julia allows you to be fast. But of course, like all statistics, there is a lot hidden by statistics, right? So I want to spend a little bit of time digging down into this idea behind performance, right? What is it that we mean when we say that Julia is fast, right? So this is a set of simple benchmarks around adding numbers, right? So there's a simple group, as trivial as you get, that adds numbers. We test this by adding I think about 10 million numbers, an array of 10 million floats, and we add those 10 million numbers using many different languages and paradigms, right? So we see that, if you look at the results at the bottom half of my screen, you see that there are sort of three uh, groups, right? So one is Julia handwritten and Julia built-in, uh, Python NumPy, and C with minus F fast, right? They are about 7 seconds, 8 seconds, right? That's a similar group. And if you run it yourself, you will get this grouping, but the ordering within that group might be slightly different. But Python might be a tenth of a millisecond faster than Julia, or vice versa, as it is in this case. So all these numbers are in milliseconds, right, for adding 10 million numbers. And then there is Julia handwritten in C, which is about 14, 15 seconds. And then there is Python built-in and Python handwritten, right? And so you will see that NumPy is about as fast as it gets, right? And C with minus F fast, which actually does SIMD, Julia handwritten with SIMD, they are all sort of as fast as it gets. And this is what we mean when we say that Julia is almost as fast as C. And you will see that NumPy is also almost as fast as C, right? So why would you want to use Julia as opposed to Python NumPy? Well, the reason in my mind is that NumPy is actually still written in C, right? And the add method in NumPy, right, the add function that adds arrays of things, works only with a certain set of inputs, right? There is one version for integers, I imagine, and there's one version for floats, and maybe there are a few others for a few specialized types, right? But the Julia sum that you see in the code above is just a simple loop that works for whatever the type A is, right? It could be integers or floats, it could be rational numbers, it could be complex numbers, right? And in Python, in NumPy, I'm not sure if it has support for complex numbers, but I certainly think it doesn't have support for rational numbers. But if you have a complex number, if you have an array of complex numbers, you typically in Python would store them as arrays of real numbers and arrays of imaginary parts. And you would then call the sum function twice separately. And so if you have to loop, you have to again loop across two different arrays, right? And so this ability to write very high level code and yet be fast is possible only in Julia. And that's our opinion, and that's why we write Julia and we are fans of Julia, but that's the difference, right? So yes, NumPy is fast, but NumPy only works for certain set of types because NumPy is written in C. And that's the same with R, right? If you add us 10 million numbers in R, you can still get very fast performance, but again, that will be for limited types. If you write, type agnostic code in Python, which is, a handwritten loop. So this PySum A that I've written, that will work for, that is duck typed, and that will work for any type of A. But you will see that the performance of that loop is really, really slow, right? So while NumPy is fast, a type agnostic duck typed loop in Python is very slow, while in Julia, a duck typed loop is still very fast, right? And that's the key benefit of Julia. Okay, so that's about as far as what I wanted to say about Julia itself. I will just end by quickly going through a few examples that people have used Julia for. There's work going on in building energy efficient models. Again, this leverages our deep learning and differential equation libraries, putting them together to model energy efficiency. So, energy efficient heating systems or air conditioners. There is work in predicting drug efficacy, efficacy, and that's again built on our differential equation models. There is work going on optimizing battery-powered aircrafts. This uses differential equations and chemistry models that have been handwritten using neural surrogates. That's some exciting work going on at CMU. There are companies working on GPS-free navigations for drones. There was a JuliaCon talk on this if you're interested. Celeste was a huge model to analyze telescope images. This actually was the first dynamic language that ran at petaflops on a supercomputer, right? There is Klima, which is a new climate model being built at Berkeley that again uses Julia for very large scale compute. And then there is personalized medicine, which people at Pumas are doing that analyzes medicine efficacy for individual patients, right? So that's really what I wanted to talk about. There were a few questions, I think.
Right. There is a, thanks for the talk, by the way, Avik. It's really cool.
Thank you.
I'm at least convinced enough to give it a go on like a Saturday or a Sunday that's super boring.
Yes.
So one of the questions we have is like the one you would most expect on a Python major conference is that would it be possible to integrate Julia code into Python?
Yes.
And I would like to add on top of that, maybe you can give us also your view from the strategy point of view, how you proceed further future development with respect to the ecosystem that's there of Python.
Yes. So so Julia has amazing C interop, right? So you can call into C SOs or DLLs without writing a wrapper or without even a .h file. And we have built a Python interoperability on top of that. So there's a package called Python, which makes it really easy to call Julia packages, Python packages from Julia. You can install Conda from Julia, install libraries, and just call SciPy functions. That works really well. A lot of people use Matplotlib, which is an amazing charting tool, and so you can call Matplotlib with Julia data, and that does zero copying data. And so having a multiple languages in your environment is very common, and we fully support that. You can do the reverse. You can call into Julia from Python. So you can have a function defined in Python. You can have a differential equations defined in Python, and you can use Julia's differential equation library to actually solve it, right? That works. You can do callbacks between Julia and Python. That works very well. There's a site, suppose a follow-up from Tom saying, when would you not use Julia? Well, personally, never. You should always use Julia, but that, of course, is not practical in most cases. And so, we have built a huge amount of interoperability libraries. I personally maintain our Java interoperability library that allows you to call Java from Julia and vice versa. There is a library for R. There are, in fact, packages on CRAN that use Julia behind. So, there's an R interface and you can use R data, but it uses Julia to actually solve a GLM, right? And so that works pretty well. So the answer is, it depends on your environment. If you have a Julia, pure Julia environment, use pure Julia. And if you have, a mixed environment, you can use a mixed set of libraries. And yes, Jorge, you can call Julia from Java using Java call. You can do that as well, both ways.
Right, cool.
And one last question, you can compile Julia to a native library. Takes a while, but it does work. And I think that's time. So thank you. I'll be on Discord.
Thanks a lot. Thanks a lot, Avik. And we really appreciate you giving this talk all the way from London.